speaker is Escamilla. He's going to tell us about model-independent reconstruction of an interacting dark energy.
First than anything, thank you to the organizers for the space and the time for me to speak about my work. I'm going to talk about reconstruction of an interacting dark energy model using a model-independent approach. So the general outline of the talk will be first a little recap of the problems of lambda CDM and what is a reconstruction. Then I will talk about what is an interacting dark energy model. And then I will talk about how our reconstruction works, and then the conclusions that we can obtain from these types of reconstructions. So first, a quick recap. We know that there are problems with lambda CDM, and one of the main ones that I want to try to attack is that we know nothing about the nature of both the dark matter and the dark energy. We only know that they made around 95% of the universe according to lambda CDM, but we have no idea how they work or if there should be an exotic component, something we don't know yet. So we want to try to attack that problem. We, of course, have another problems such as the H0 tension, S8 tension, and others. So we know there's something wrong with the dark sector. We are going to use an approach known as a reconstruction to try to find a possible solution, or at least to find a way to find a possible solution to this type of problems. So what is a reconstruction? As its name suggests, it's a numerical method that uses data or observations to reconstruct a physical quantity. And we generally classify them in three classes. It's parametric, non-parametric, and model independent. So what is a parametric reconstruction? This is one of the most used one in the literature. For example, let's say we want to reconstruct the equation of state right here for the Friedmann equation. We can select a parametric function such as, for example, this is one of the most famous ones, CPL. You can also start proposing some more exotic ones that have logarithms or sine or cosine functions. You can also propose Taylor expansions. And you can basically choose any parametric shape you want to study a certain behavior for the equation of state. For example, if you want to see if the equation of state oscillates, you can propose something that has a sine. You can also try to find a behavior that is like a logarithm growth, or well, you can generally choose anything you want with this type of reconstructions. Then we have their counterpart. They are called non-parametric reconstructions, and they are very different from the parametric ones, since they do not have parameters, or at least they don't have parameters that you need to feed with data. And they have much more freedom, and they are completely data-driven. They don't care about the functional form or any of those type of things. They carry a risk of overfitting the data sometimes, but that can be solved with some other methods. One of the most famous ones are the Gaussian process. There is another popular one called Loess-Simex, and another popular one is the neural networks. Here is an example of two non-parametric reconstructions for the Hubble parameter. The first one here in the left, is with a Gaussian process. A Gaussian process is basically you have a set of data, in this case the cosmic chronometers, and you try to fit a Gaussian curve to all the available data, and it gives you the most probable Gaussian curve that has to predict this set of data. When you use a neural network, like in this slide on the right, it's a little bit more complicated, and you cannot really talk about 1 sigma or 2 sigma because there's really a different type of statistics and processes behind the neural network, but you can get something similar to the plot in this side. And this can help you get an idea on how, according to the data, the Hubble parameter has to behave, and you can then start making some assumptions or predictions with this. Then we have the model-independent reconstructions. These reconstructions are like a mix between the parametric and non-parametric. They can be seen as a branch of the parametric reconstructions because they do have parameters that you need to fit with data, but we don't care about the functional form. We only care about like the final result that you get after making parameter inference. Some of the most popular ones in literature are the Beans reconstruction, the Fourier series, the Padé approximant, and another one called nodal reconstruction. In this work, I will talk mainly about the Beans, and also we will talk about another one that involves a Gaussian process, but in a kind of different way to the non-parametric approach. So what is a Beans reconstruction? Basically, you have a function like this, which is a bunch of step functions that are joined via a hyperbolic tangent. You have only one, well, you have as many bins as you like. It's this wi here, which in this case, this will be the functional form for, let's say, an equation of state. And you have a smoothing parameter in this part right here, which governs how smooth is the transition from one bin to another. Here is a visual example. Let's say that we have 4 bins. They will be equally spaced in redshift from 0 to 4. And let's say that we start varying the position of the second bin. We have here 4 examples on how this will look with different positions and how it will look with a different smoothing parameter. The idea is to find the optimal positions of each of the 4 bins so that we can, well, at least the optimal positions preferred by the data that we are going to use for the reconstruction. The other model-independent reconstruction we used is known as a Gaussian process, but as an interpolation, not as a non-parametric reconstruction. So it's different than the approach I mentioned you earlier. It's more similar to this graph right here. It's also similar to the bins reconstructions in the sense that we have, let's say, we have 10 points, or we call them nodes. These nodes can also vary their position. Then we do a Gaussian process to them in this manner, like in the middle figure. But when you have a Gaussian process, you have a mean curve, which is the black line, and you have a 1 sigma deviation or 2 sigma deviation, which is the gray area. We do not care about the gray area. We only care about the mean position of the curve, which is the black line. And then we are going to find the optimal position of these points according to data to fit our reconstructed function. As a visual comparison between the bins and the Gaussian process, as an interpolation, we have this graph here. Let's say we have 8 bins or 8 nodes in this case. They have the same position, but you can see that the green line, which is the Gaussian process, presents some differences to the bins approach, and also the bins approach presents some differences depending on the smoothing parameter. And in this case, we're going to use this with the interacting kernel for an interacting dark energy model. So what is an interacting dark energy model? We usually assume that in the continuity equations for dark matter and dark energy, they are conserved separately. They are equal to 0, but we don't mess with this very much. But there is nothing stopping us from adding an interaction between these two, within dark matter and dark energy. You can introduce here, for example, a Q, and here a minus Q, which means that there's going to be energy transfer between dark matter and dark energy, and depending on the sign of Q under this sign convention, when Q is positive, you have a transfer from dark energy to dark matter, and when Q is negative, you have a transfer from dark matter to dark energy. Some examples in the literature that have also used model-independent reconstructions. I think one of the first ones, and also one of the oldest ones, is this one by Kai and others, where they reconstructed this delta right here. This delta has to do with the interaction in this way. These are the continuity equations he reconstructed, and he used the bins approach, varying the number of bins. In this part, he used 3, 4, 5, and 6, and he found that with the data available at that time, which was the supernovae from Union and DR7 for BAO, he found that it was possible that the interaction kernel could oscillate a little bit, so it would change values from positive to negative, so that would imply a change in the energy transfer from dark matter to dark energy and vice versa. Another important previous result, is the one by Bonilla and others. He used a non-parametric approach, a Gaussian process, to reconstruct also this delta here, which is the interactive term for the interacting dark energy model. And he also found something similar, also a kind of transition between signs for the interaction. So we wanted to try to find something similar with our different approaches and with more updated data. So now I'm going to talk about our reconstruction. This was made in collaboration with Osgur Akarsu, Eleonora Di Valentino, and Jose Alberto Vázquez. So how are we going to do our reconstruction? We have our continuity equations. We introduce this effective equation of state for both the dark matter and the dark energy. These effective equations of state are these right here. We are also going to see how how this affects our final density for both dark matter and dark energy. And the quantity that we are going to reconstruct is this capital pi right here. It's an a-dimensional interaction kernel. And then we put this in the continuity equations. We have these final continuity equations that are numerically solved, and they are in function of the redshift. And then after numerically solving them, we can put them in our Friedman equation and analyze what happens to the interaction. The data we use for this reconstruction is the 31 cosmic chronometers of the usual catalog of 31, the Pantheon Plus supernovae catalog, and also DR16 for SDSS and EVOS BAO distances, and also Lyman alpha, high redshift Lyman alpha BAO data. We also use our own parameter inference code. We call it Simple MC. You can find it here in Jose Alberto's GitHub. So now I'm going to talk about the results of our reconstruction. First, we have 4 cases for our reconstruction. In 2, we use the beans approach. In 2, we use the Gaussian process approach. And in one of the beans and in one of the Gaussian processes, we fixed the parameter W0 to -1. This parameter is this one right here, this WD, which would be the original equation of state for the dark energy if we wouldn't have this interaction term. In 2 of the cases, we fixed it to -1, and in two of the other cases, we left W0 to be a free parameter. So these are the results. Instead of reporting pi, we are reporting this quantity right here, which is basically pi, but we are dividing it by 1 plus c to the power of 3, so that it's easier to visualize. And you can see that with the beans, which are the first 2 cases, we have in the first case where W is not allowed to vary, we have like a less constrained and less oscillating behavior. But when we allow W0 to be free, we have a much more well-behaved function, a little bit at least. And we also find a similar transition to the other 2 papers, where we are allowing a transition from positive to negative, then again to positive, and it's preferred by at least 1 sigma preference over lambda CDM. We have similar results with the Gaussian process approach here in the case 3 and 4. And one of the interesting results in this paper is that after recovering the interaction kernel, we can then recover the effective equation of state for dark energy. These are the 4 equations of state. And it's kind of hard to see, but there is a 1 sigma preference to have an asymptote in a discontinuity here in around redshift 2 for the 4 effective equations of state. And this behavior for the effective equation of state is also characteristic of something that Osgur already told you about, which is a sign switching cosmological constant. These are the reconstructed energy densities for dark energy, and we can see at least a 1 sigma preference for a sign switch before around 1.5 or 1.8 in the redshift. And this is reminiscent of a previously obtained result that we obtained like 2 years ago, I believe. In this paper, we reconstructed the dark energy density, but directly using beans. In this case, we used 21 beans to reconstruct it. And after reconstructing it, we can get the associated equation of state, and it has this shape right here. It's kind of hard to see from here, but there is a discontinuity here that goes to -infinity, then recovers from +infinity and comes back here. This is also characteristic of a change in sign in the cosmological constant. Then we have here the constrictions of our parameters, our beans and our nodes. One interesting result here is that when we allow W0 to vary, like in this part right here, we see that, when W0 is fixed, we have 2 tightly constrained parameters here in this part, but when we allow it to be free, we allow it to be more free to our first bean or node. So maybe we have both an interaction and also a dynamic equation of state for dark energy. Maybe it will be interesting to explore that type of models. And also, as we expected, the last 2 parameters, the ones in the positions 4 and 5, are not that well constrained because our datasets are not so we have basically no data in this region right here. So it's what we were expecting. So other important results, we also do not fix the Hubble tension, but we also were not expecting to. Well, we alleviated a bit, but only because the uncertainty became a little higher compared to lambda CDM. Also, we have a better fit to the data as expressed here by the chi-square. The best one was this one right here, which is the Gaussian process when W0 is allowed to vary. And also, unfortunately, our Bayesian evidence still favors lambda CDM by a long margin. We have, according to Jeffrey's scale, almost strong evidence against our models, but we were also expecting that because we are adding 5 extra parameters on top of the, well, in this case, we are adding 6 extra parameters on top of the usual lambda CDM parameters. So finally, the conclusions of this work. Our data that we use for the reconstructions seems to prefer an oscillating interaction, which implies a change in the flow of energy transfer from one part of the dark component to the other. Also, that the interaction we found in a model-independent way seems to prefer a change of sign in the dark energy density, which is also slightly preferred by around 1 sigma over lambda CDM. Bayesian evidence is still preferring lambda CDM, which is, of course, bad for our reconstruction, but it's still, we were expecting that result. And finally, maybe we can use these results, since we are using a model-independent reconstruction and not a parametric reconstruction, we can use our results to maybe propose a future interaction that also oscillates, has less parameters, so it has a better chance against winning against lambda CDM, but it will also try to reproduce the results we found here. And that will be all. Thank you.